Good morning students. Today our class is about electric flux. Okay, so already we have some basic idea about what is electric field and electric field intensity. Okay, so electric field means what? Electric field means what? It is a effect of charge. Okay, it is a effect of charge around it. Okay, so this is the electric field and already we learned that it is a vector quantity. Okay, vector quantity. Okay, and electric field intensity is a vector quantity. Okay, it is a electric field means effect of charge and electric field intensity is a vector quantity. Okay, so now here already we have some formula, that is electric field intensity is equals to what? The force which is experienced by the charge. Okay, so here the force experienced by the charge is the electric field intensity. It is a vector quantity. Okay, and okay, so now here we have to know about what is electric flux. Okay, so here electric flux means it is a quantity. Okay, it is a quantity. Quantity means it is a number. Okay, it is a number. So which number it is? Okay, so here we are sending so many. Already we learned that the parallel rays which are coming from the infinite source. Okay, so when we are considering the parallel rays and they are equidistant from each other and they are having the same density and the same direction, so that is the uniform electric field. Okay, so uniform electric field means it has same direction. Okay, now here I am sending the electric field like this. These are the field lines which are coming from some infinite source. Okay, now here I am placed one area like this. This is my area. Let us consider this is the area A. Okay, and this is my area B. Okay, now see here, this is the area 1 and this is the area 2. So from the area 1 here, how many lines are passing through the area 1? That is 1, 2, 3. Okay, so this is 3 lines are passing through the first area. Okay, and here only one line passing through the second area. So that is the area B. Okay, so here 3 lines means the 3 electric field lines which are passing through this area, that is the 3 lines. Okay, so here only one electric field line which is passing through the area, that is the B. Okay, so here electric flux means quantity means it is a number. Okay, so here three number of lines. Okay, so that is the quantity of lines are what? 3. Okay, so that means here electric flux means the number of lines, the number of electric field lines which are passing through the particular area is the electric flux. Okay, here also the number of field lines which are passing through the particular area is the electric flux. Okay, so here in this case, in this area A case, okay, so the field is stronger. Okay, in the case B, the field is weaker because only one electric field line is passing through this area. Here 3 lines are passing through this area. So compared to the area B, here the stronger the electric field in the case of the area A and the weaker the electric field in the case of the area B. Okay, now see here, electric flux is a quantity means it is a number means only magnitude. Okay, not the direction. Here I am not giving any direction for the lines. Okay, so here I am saying that only 3 lines are passing, only one line is passing, so the number of lines only I am considering. Okay, I am not considering any direction. So that's why here electric flux is a quantity. That means here it is only tells about the quantity. Quantity means what? It is only magnitude. It has only magnitude. It has only magnitude, not the direction. So it has only magnitude means the electric flux is a scalar quantity. Electric flux is a scalar quantity. Okay, so here electric field intensity is the vector quantity and electric flux is a scalar quantity. So here what is electric flux? The number of electric field lines, which are passing through particular area, passing through the particular area. It has no direction, it has only magnitude, so that's why it is a scalar quantity. So electric field intensity is a vector quantity, and electric flux is a scalar quantity. Okay, so here let us consider one so here we are having some window. Okay, so these are the sun rays which are coming from infinite place. Okay, so here sun rays means let us consider these are the rays like this. Okay, so here how many rays are enters in this window, so that is the electric flux. Okay, so if I am placing the window like this is my window, and here the field lines are, the sun rays are coming from these directions. Okay, so let here the opening of the window is like this. So here as the opening is like this, so the three lines are entering through this window. Okay, so here the opening is like this, no? So here I am placing the window like this, so here there is no field line, there is no rays or enters through this window. So here the field lines enters through this window is what? 0. Here the rays which are enters through this window is what? 3. Okay, so that means if the air direction, okay, the rays direction is like this. Okay, if I am placing the window like this, so the air will be enters, and here we are getting some flux. Okay, if the air direction is like this is the air direction. If I am placed the window like this, so then there is no flux which is enters through this area. So here the flux is 0. So that means here the flux mainly depends on the number of field lines which are entering through this particular area, and also here the direction of the field lines which are entering through that area. Okay, so that particular window. Okay, so that means here the number of field lines which are entering means this will depends on the intensity, the electric field intensity of that air. Okay, so that means here the flux mainly depends on two things. One is intensity of field or intensity of air, that is the direction of the intensity of field, and another one is direction of the air. Okay, so that means here intensity means the number of field lines which are entering through that area, and direction means in which direction they are coming. Okay, so here the number of field lines means it is a number, the direction means it is a okay, it gives some orientation of that field. Okay, so that means here we are having some magnitude and here we are having some direction. So that means it mainly depends on what? Electric field intensity. Okay, and what here we are placing some area, no? So this is the area. So the correlation between the electric field intensity and area gives the flux. Okay, so let us consider here we are having some pipe like this. This is the, let us consider this is our pipe. Okay, so here we are sending some water. So these are the water. Okay, now here I am placing one pipe like this. Okay, so here this is the bucket. Okay, now the water direction is like this and this is the area. Okay, so here the entered water is how much, just consider the two, here the quantity only 1 liter water are entering through this pipe. Okay, so now here I am placing the water, this is the bigger pipe, and here we are sending maximum quantity of water. So this is the quantity of water coming, and here I am placed the greater area of pipe, and this is my bucket. Okay, now see here we are sending the maximum quantity, here we are sending the less quantity. So that will depends on what, the area of the pipe and direction of the water. Here also the direction of the water and area of the pipe. Okay, so here we are getting so much quantity. Okay, so that means this quantity, the water in the bucket will not depend on the direction, it only has a quantity, it has only quantity, that is the magnitude. But before filling this, here the water has some direction, and the quantity, magnitude, and here it will also depends on the area. Okay, so that means it is the area, and let us consider this water has some direction and the quantity means, let us consider that is the field intensity. Okay, so electric field and area gives the flux. Okay, so this is about the electric flux. So here electric flux linked with the electric field intensity and the area, electric field intensity and area. So here I am writing the area as a vector, I am considering that area as vector. Why? Because see here, if I am sending the water in this direction, so if I place the area, if I place the area like this, okay, so this is my area, so then there exists some flux. Okay, if I place the area like this, then no water coming from this area, so here the flux is 0, here we are getting some flux. Okay, so that means depend on the direction of the area also, here the electric flux depends. Okay, the electric flux changes. Okay, so that's why here we are considering that area as a vector. Okay, so now area as a vector means it has magnitude and direction. Okay, so area magnitude is what, let us consider, we have to consider one area. So if this is an area, so let us consider this is the length. Okay, so this is the breadth, then area is what, the magnitude of area is what, length into breadth. Okay, so see here we have to take the angle theta. So if it is a theta, so here it is a breadth, then opposite to breadth. Okay, so that is b sin theta. Okay, adjacent to breadth is what, b cos theta. Okay, so now here L into b, no, here L into b. Okay, so that means here this is the L and this is the b. L and b are perpendicular to each other. Okay, so L and b are perpendicular, so L and b are perpendicular. So that's why as L and b are perpendicular, so area is equals to what, length into breadth is what, b cos theta. Okay, so that is b cos theta. Okay, so here as LB cos, sorry, this is the length and the perpendicular one is b sin theta. So here LB sin theta. Okay, so here we can written as L cross b. Okay, so why L cross b? Because for the dot product we are getting the, if L dot b is there, then we have to write LB cos theta. If L cross b is there, then we have to write LB sin theta. Okay, so that's why here L and b. Okay, so that is, it is a vector and it is also a vector. Okay, so then cross product of two vectors also a vector. So that's why area is considered to be a vector. So if area is a vector, then the magnitude of the area is what? Magnitude of the area is LB sin theta. But the direction is what? Direction is always normal to area. Always normal to area. This is the direction. Okay. So here we have to take, if E, let us consider if this is an electric field. Okay, so if this is an area, okay, now electric field direction is in this direction, and we have to take the area vector always normal. So this is the normal. So here area vector. Okay, so now see here, E and A, okay, both are in same direction. E and A vectors are both are in same direction. Both are in same direction. If both are in same direction, we have to take the dot product. We have to take dot product. We have to take dot product. So that's why electric flux is equals to what? E dot A. E dot A. So that is EA cos theta. EA cos theta. So here EA cos theta, no? So that's why if we are taking the dot product of the two vectors, okay? So dot product of two vectors gives what? Scalar. So that's why here electric flux is a scalar quantity. Electric flux is a scalar quantity. Okay? So this is about the area. So here area, we are considering the area as a vector. Why? Because it has a magnitude and direction. Magnitude is we have to take LB sin theta, and direction is it is always normal to the area. If it is normal to area, if we are considering area as a vector quantity, let us take this is an electric field. If we are placing the area here, so electric field and area both are in the same direction. If both are, why E and A are in same direction? Because A is always normal to the area. Okay, so the direction of the area is always normal to the area. So this is the normal, and here this is an electric field direction. Both are in the same direction. So if both are in the same direction, we have to take the dot product. Okay, so that's why E dot A is equals to EA cos theta. So as those are the vectors, if you are taking the dot product, then the dot product of two vectors is what? Scalar. So that's why electric flux is a scalar. Okay, so here area is a vector quantity. Okay, now here if you are taking that electric field and area as a if electric field, okay, electric field is uniform and area is a plane area. Here we taken that electric field is a uniform and area is a plane area. Okay, so if we have some more situations that if electric field is not uniform, if E field is not uniform, electric field is not uniform, and area is a not regular area, so that is a irregular area. Okay, so here we are considering that electric field is a uniform electric field. We place a one plane area which is a regular, which has some regular pattern. So then we find the electric field as E dot A. Okay, now here I am taking that electric field is not uniform. Let us consider that here is the charge. Okay, now this charge have some effect in all direction. This is the electric field which is due to this charge. Now here I am taking one irregular surface. Okay, so this is my irregular surface. Okay, see here, this is at this point. At this point, let us consider as this is an surface. At this point, this has a small surface area. Okay, now here electric field direction is this direction, and this is my small area. Okay, so as it is a area, and here the normal to this area is what? This one. Okay, so this is the area vector. So here we are having some angle theta. Okay, now here also this is an electric field Okay, so here we have to take the normal. So this is an area vector. So here also we are getting some angle theta. Okay, so that means here the electric field linked with this area, electric field linked with area gives the electric flux. Okay, so here the flux linked with small area is what? Here we are taking small area. Let us consider this is the area 1. Okay, so this is a small area. Let us consider dA2. This is a small area dA3. This is a small area dA4. Okay, now here the electric field linked with this small area is E1 and this is E2 and here E3 and here E4. Now we have to get the flux, total flux. Okay, so now flux linked with now for first linked with the flux always denoted by the phi. Okay, so here the electric flux always denoted by phi. Okay, so now if the flux linked with the first area, let us take first area, so that is the flux 1 is equals to what? Already we know that the electric flux is a dot product of the electric field intensity at that point and which is passing through some particular area. No? So that area is what? Small area, that is the dA1. Okay, now so here we are getting some angle theta, so that's why here is the dot product, so we have to take EDA cos theta. This is the, here we have to take the two vectors. Here we have to take only magnitude. This is the vector rotation and this is a scalar, that is the magnitude. Okay, now here the flux at the second small area. Okay, so here we have to take the small area. Here we are considering the small areas. Why? Because it is a continuous body and irregular body. If it is a regular body, the area at any place is same. So that's why we have to take the total area as the A. But here it is a irregular body, so we have to take the electric field at different points. Here the electric field is different, here the electric field is different, here the electric field is different because it is a irregular body. But in this situation, here the electric field electric field at every point is same for the regular area, because the electric field direction is same. Here the area is a regular area, so here both are in the same direction always. But in this situation, at this place the electric field is different, at this place the electric field is different, at this place the electric field is different. Okay, so that's why here we have to take some, and here the area vector also making some angle theta with the electric field. Okay, now at the flux 2, this is a small flux, so d phi 1, this is a small flux at the d phi 2, so E bar, this is a E1, this is a E2 and dA2, so that is EDA2 cos theta. Okay, so here it is making an angle theta 1, here it is making an angle theta 2. Okay, so now like that. Okay, if you are taking the n elements, then En dA3. Okay, so that is En dAn cos theta n. So now I want to take the total flux over the irregular area, so that's why we have to take the summation. Okay, so summation means it is a continuous body. So here we let us consider the dA, the small area tends to 0. If small area tends to 0, then we have to take integration. So the total flux is equals to what? Integration over small flux. So that is equals to integration of small fluxes means the integration of E and A and cos theta. A cos theta. So this is for the irregular surfaces. So here electric flux is defined as what? Electric flux is defined as what? The electric field lines which are passing through particular area. So here the number of field lines, the number of field lines passing through particular area. Okay, so here we are considering as area as a vector. So electric flux is a scalar quantity, it has only magnitude, and here for uniform field, for uniform electric field and regular area, so the electric flux is equals to what? Electric flux is equals to E dot A. Okay, so here area is a vector quantity, okay. Now for non-uniform electric field, and irregular areas, we have to take total flux as the E integration of E dot dA. Okay, so that is equals to E dA cos theta. Okay, and here the so this is about the electric flux. Now here electric flux through a closed surface, we have to take electric flux through a closed surface, electric flux through a closed surface. Okay, so in this situation we have to take the uniform electric field. This is the electric field direction. Here we are taken one area, so area vector is like this, so both are, then theta is equals to 0, so that's why EA. Okay, so here we are taken one charge and the electric field is non-uniform, so and the area is irregular. At this point, this is the electric field direction and this is the area vector, so here we are getting some angle theta. Okay, now electric flux through a closed surface. Closed surface means closed from the all the sides. So all the sides means we have to take sphere or cuboid, all these are the closed surfaces, and cylinder also closed surface. Okay, now here electric flux through a closed surface, no. So now let us consider, I am taking the uniform electric field. This is my electric field. Now here I placed one cube. Okay, so this is my cube I placed here. Okay, now see here, this is a closed surface and it is having 6 surfaces. So now I already told that area vector is, the direction of the area is always normal to the surface, Okay, now see here, this is the electric field direction. Okay, now for this surface, let us consider this is the 1, 2 and this side. Okay, so this side surface is 3 and here surface is 4 and that is 5 and this side is 6. Okay, now for the first surface, this is the electric field direction and this is the first surface, no, so the area vector is normal to the first surface, so this is the area vector. Okay, so here angle theta is what? 0. E and A both are in the same direction, so it first surface I want to get the total flux through this closed surface. Okay, so phi t. Okay, so now here for the first surface, now see here, through the first surface I want flux. Okay, so flux through the first surface is equals to E and A both are in same direction, so theta is equals to what? 0. So as EA cos theta, no, so theta is equals to 0 means, so cos 0 is what? Cos 0 is 1, so here we are getting the flux as the EA. Now for the second surface, now second surface, this is the second surface, so normal to the second surface area vector, so this is the area vector. Now this is the electric field direction, so see here we are getting the 90 degree. So that means theta is equals to 90. Then cos 90 is what? 0. Cos 90 is what? 0. So as cos 90 is 0, then phi 2 is equals to EA cos 90. So cos 90 is 0 means this total flux through the second surface is 0. Next third. At third surface. At third surface. Okay. So at third surface, here this is the area, no? So here area vector is normal to the surface. So here this is normal. So here we have to take the area vector normal to the surface and always outward normal. We have to take always outward normal. So this is the outward for this surface and this is the outward for this surface and this is the outward for this surface. So for the third surface, and this is the area vector, and here this is the electric field vector. So here this is the area vector and this is the electric field vector. So theta is equals to what? 180 degree. Here theta is equals to 180. Then cos 180 is how much? Minus 1. So then phi 3 is equals to what? EA cos 180. So that is equals to minus EA. Now at fourth surface, this is a fourth surface and outward normal. So this is the A vector and this is the electric field vector. So here we are getting 90 degree. So theta is equals to 90 degree. So then phi is equals to EA cos 90. So that must be is equals to what? This is a 0. So here flux is 0. Now at fifth surface. Okay. So fifth surface is that side face. Okay. So at that also the area vector is like this and electric field is like this. So there also we are getting theta is equals to 90 degree. So then phi t is equals to what? 0. Next, at sixth surface. At sixth surface also we are getting theta is equals to 90 and phi t is equals to 0. So then now the total electric flux through closed surface cuboid. What? Phi total is equals to phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 6. So that is equals to phi 1 is EA and phi 2 is 0, phi 3 is minus EA and phi 4 is 0, phi 6 is 0. So here we are getting the total flux as the 0. So then the total flux through a closed surface is 0. So the flux through the closed surface is what? Closed surface is 0. But it may be 0, may not be 0. Always it may not be 0. Sometimes it will not be 0. This is given by the Gauss law. Okay. So let us consider this is the conductor. Now here I placed one closed surface here. Now I want to get the electric flux through this surface. Let us consider here at this point the electric field is different and at this point the electric field is different. Okay. Let us consider this is a first surface and this is the second surface and this is the third surface and this is the fourth surface. Now electric field at first surface and electric field at third surface is different because here the electric field intensity is more, here the electric field intensity is less because electric field is depend on the inverse square law. So as R is greater, then electric field will be okay. So at greater distance the electric field intensity will be decreases. So here the electric field intensity is less and here the electric field intensity is strong. Okay. So that means as here some variation in the electric field intensity, so as we know that the flux is equals to electric field intensity into area. Okay, for the greater electric field intensity the flux is maximum. For the lesser electric field intensity the flux is minimum. Okay, so that's why always the flux through the closed surface may not be zero, but but for some fixed surfaces like sphere and the cube. Okay, so through that surfaces only we are getting the total surface through closed surface is zero. That is also depends on the electric field intensity through the area. Okay, so that's why here the electric field intensity, so the total flux, always we have to take integration over E bar dot ds bar. We have to take like this. Okay, so this is the flux linked with closed surface. Okay, so it may not be zero, it may be zero. Okay, so that will depends on the electric field intensity through that surface. So that's why here it's for the particular surfaces only we are getting the total flux through that closed surface is zero. Okay, so this is about the electric flux. Okay, so depending on, so here if we know the electric flux, then only we can solve the Gauss applications. Okay, so first we have to know, by using this electric flux we can derive the Gauss theorem. Okay.